Welcome to the final exam, question number 12. And this one's pretty straightforward, so we'll just go up and start labeling, and then from there you can look at and see which one matches up respectively. Alright, so we know this is a stress-strain curve, and hopefully you know that this is stress, this is strain. I guess they could be inverted. You could have strain up here, but then it would look different. You would see it go up, and then it would go. This is the elastic region. Elastic region. This is plastic. My handwriting and my spelling are falling apart. Alright, so we know this is stress and strain. So let's see if we can get rid of something. And it looks like A, it says unit strain, so we know that's not correct. So get rid of A. I'm sorry. A, B, C, D. So we can get rid of A. Everything else has unit stress first, which we know is A, correct? B is going to be strain, so let's make sure all these are strain. B says unit strain, unit strain, unit strain, okay. And then the next point is C, so elastic limit and yield point. And this is probably where it gets a little bit more difficult to know the difference between the elastic limit and the yield point. And the difference between those is what this is all about. Alright, so the elastic limit and the yield point. And the elastic limit is, this is going to be this is obviously, the slope is rise over run, like any slope is, and it's going to equal constant for the elastic limit. The slope is constant, and that's kind of true for the yield. You could say it's so close where the yield point is actually, I'll just tell you, the yield point is right above it. And that's actually where the slope flattens out. It stops when you stress it. It's the point where it'll start moving without stressing it anymore. It'll start the strain will increase without stressing it anymore. Where strain goes up despite constant. Oh wow, that doesn't look like it's constant. Alright, let's try again. Constant. Stress. And this is probably not exactly constant stress. I mean, it might be at a point where you say, okay, well, you know, I'm barely increasing the stress and my strain is just going skyrocketing. And I don't know if it's if I would say that's an exact point where this has to happen, or close to constant stress, despite close to. And I think that makes sense. The elastic limit is exactly the point where this will behave elastically, and in steel this is more of a defined shape. So this is Hooke's constant, I guess. Hooke's law says it's stress over strain, so it will do this, and then once it starts off that slope, so if I want to zoom in, I'll zoom in right here. So you're going up at a constant slope, and then all of a sudden it starts taking off like that, and then all of a sudden it's like that. So I would say this would be your elastic limit. I'm going to abbreviate it EL, and this would be your yield point, where that piece of metal just starts, it will deform, and you will notice it deforms. Alright, so let's see which ones that is correct. As I said, it's the yield point, this is the elastic limit. And C is elastic limit. Oh, well there we go. B is the only one that has the elastic limit as number, or letter C, as opposed. And this is also the ultimate strength. This is the point right here, is ultimate strength. And that you can do ultimate strength type design, plastic design, but we're not going to get in that. We're in elastic design, so we're going to be in this region right here, because once you get past that region, you start getting deflections that aren't usable in a service-based type situation. All right, I hope that helped you out, and I will see you on question number 13.